Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on October 13th, 2025, just yesterday. The key move swaps the old VAE for Representation Autoencoders and delivers standout ImageNet scores, 1.51 FID at 256 by 256 with no guidance, and 1.13 at both 256 by 256 and 512 by 512 with guidance. The paper is titled Diffusion Transformers with Representation Autoencoders, and the implications for model training are quite significant. This paper shows faster convergence using high-dimensional semantic latents, a lightweight wide denoising head, and no extra alignment losses. On Hugging Face, you will find a RAE Diffusion Transformers collection, links to checkpoints and docs, plus basic usage examples. No parameter sizes listed, and no hosted inference yet. Alright. Figure 1 makes the point that switching to representation autoencoders drops Fréchet inception distance, which measures visual realism, so lower is better. The plot contrasts prior VAE latents with the new high-dimensional latents and shows consistently lower scores. The blue markers at the right highlight DiT/DH on Dino v2 encoders, which sits near the bottom because samples look more faithful. The dotted circle indicates further gains with auto guidance. Alright. Figure 2 shows that representation autoencoders make the pipeline simpler and cheaper than the standard VAE path. Figure 2 contrasts the two setups, emphasizing that down and up sampling dominates the VAE. The VAE encoder needs about 135 GFLOPs. Its decoder adds about 310 GFLOPs, which reflects the heavy convolutional stages. In contrast, the representation autoencoder needs about 22 GFLOPs because it uses a VIT without compression. The decoder is lighter too, at about 106 GFLOPs, so overall compute drops substantially. So Table 1 shows that representation autoencoders deliver better reconstructions and stronger features than the SDVAE. The MAE base encoder reaches rFID 0.16, where rFID means the FID score computed on reconstructed images. AVITXL decoder scores rFID 0.49. The same decoder uses about 107 GFLOPs, so it stays far more efficient than the SDVAE. On representations, DINOV2 base reaches about 85% top 1 accuracy, which indicates well-preserved semantics. So Table 1 showed better reconstructions and strong features. Figure 3 shows that diffusion only succeeds when model width meets the token dimension, which here is about 768. This sanity check, overfitting to a single sample, means the model should exactly reproduce one training image. The left panel drops loss and improves quality once width reaches the token channels. The right panel changes depth, yet loss remains high, so deeper stacks do little without sufficient width. Well, Figure 6 explains that the wide diffusion head scales training more efficiently, so FID drops with less compute. This left panel shows FID decreasing as training GFLOPs rise, where GFLOPs means billions of floating point operations. The middle panel compares against VAE baselines and shows faster convergence at comparable budgets. The right bubble chart summarizes methods, with bubble size indicating compute, and the new approach sitting lowest overall. So, Table 8 reports class-conditional ImageNet performance at 256 by 256 and compares recent generators. The TT-DHXL with the representation autoencoder leads with FID 1.51 without guidance. With auto guidance, which gently steers sampling toward the class, the score reaches 1.13. The table also shows higher inception score and balanced precision and recall, so the gains look broad. A note flags rerun baselines because class-balanced sampling changed FID slightly. Wrapping up, 2 takeaways stand out. Swapping in representation autoencoders gives rich, high-dimensional latents that train diffusion transformers faster and more stably, and the wide diffusion head delivers state-of-the-art ImageNet quality with less compute. The broader implication is a simpler, cheaper default pipeline for scalable generative transformers. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.